Hello students, Ms. Slyman here with your notes on the normal probability distribution. So we looked at a few other probability density functions and we put those into charts, but one of the things that we didn't do was graph those and look at the pictures. And graphing is a lot of what we do with the normal distribution. It's one of the most important distributions in statistics, and we use them for continuous probability distribution. So variables that are continuous, they go on both directions, negative infinity to positive infinity. And they're continuous as things that can be measured: height, blood pressure, gestation times, etc. So the normal function has these, this just says probability density functions, but this is specific to the normal. So let's pretend like that first letter is an N. All right, bell-shaped curve, symmetric around the mean, and variability measured by standard deviation. Okay, this is the formula for the normal distribution. You don't need to know this formula, you don't need to memorize it. In fact, we hardly ever use it. But those of you who are maybe already thinking about internal assessments for your 11th grade, this can be a very interesting formula to look at and how it's developed, etc. So we use the variables mean and standard deviation squared is variance. So mean is going to go from negative infinity to infinity. Because this is squared, it's always going to be positive. So variance is from 0 to infinity. We show by this, we mean a normal distribution. So this is our way of saying x such that it is a normal distribution with mean mu and variance, and of course variance is standard deviation squared. All right, since it's symmetric, the way that we measure, well, we'll get to that. Since it's symmetric, area to the right of the mean is 0.5, area to the left of the mean is 0.5, and area is how we measure probability. So area under the curve measures probability. That's very important. So this specific probability distribution function, the normal probability, makes this bell-shaped curve symmetric about the mean. Another key feature is that the areas that are between one standard deviation of the mean. Yeah, so that falls at these points of inflection. Points of inflection are where a curve changes shape. So here we've got concave down, and starting at this point, it's like concave up. Yeah, we learn how to find those exactly in calculus. Right now, just know where that is. And the empirical rule, the 68, 95, 99.7, says that within one standard deviation of the mean, so on either side, one standard deviation, this area, and area, of course, is the probability. So for a normal distribution, 68% of the values are within one standard deviation of the mean. Standard deviation of the mean. Within two standard deviations of the mean, so if we go over another distance, sorry, not of the mean, if we go over another standard deviation, so that distance to about here, that's going to be the mean plus 2 standard deviations. Over to here, mean minus 2 standard deviations. So now this area, let's change colors. So if we went all the way, this whole area is now 95%. And if we go 3 standard deviations over, we've got almost 100%. Okay, here's my more specific percentages. Of course, since it's symmetric, this total bit 68% means that each half is 34%. Yeah, or if we're going to go more specifically, 34.13. Since within 2 standard deviations of the mean, I've got 95%. So half of 95.44, that would be what, 47.5 plus 22, yeah? And then we divide that in half to get these values. So you can see we've got 47.72% is in measuring from the halfway point. And then we keep going over. If we add everything up, we should get a total of 100%, right? All probability is going to make 100%. These values out here are going to be extreme outliers. So that's the introduction to normal distribution, and I'm going to come back in the next video and do this first example.